is it, I haven't been paying attention. Are we off topic?
Yeah.
Oh,
We have never gotten on topic yet.
Okay.
I think
Mike,
we
we
have
got
gotten on topic.
We need to start vibrations, but I took a reckless decision to postpone it for 20 minutes or maybe even for the Friday lecture, because I'm impressed how nice is the contact between class and instructor. This year, although you fear the homework, you have a really strong preparation. And there is a subject that I never included neither in this course nor in corresponding graduate course, but it will be really beneficial for those of you who eventually may do some practical research. It may be too much for the projects in class, but it is an important cornerstone. And since I do not have slides, I will just perform on a blackboard, doing twice as much errors. But the most important thing are the concepts. So idea is to mumble about things, derive, then mumble about vibrations, and then time will be out, right? What is this new subject? When we did
It is massive.
so when we practice practical in the box, which is a great model, how many electrons did you place there? How many molecules with one electron do you know?
One.
Can you name it?
Hydrogen
It's atom.
with one electron.
Yes.
Molecule.
How about a cation of molecular hydrogen? H2 plus.
50 plus.
Yeah.
It exists in the stars. Nebulous. No protons. H2.
Oh, H2. Okay.
atoms, they're bonded together, but they only have one.
Oh, yeah.
electron between the two of them.
It does exist, but if you look only on one electron, it a little bit limits our reach towards real chemistry, right? So there is a fact that most natural objects do have more than one electron. And by now, you are on a raging star trajectory, but objectively, we do not know anything except free space and particle in the box. But we need this concept. So can we try placing more than one electron into the box?
Yes.
Try.
I don't think it's a.
So here's the question. Which orbital second electron will take?
For H2 plus or just.
No, for particle in the box. Suppose you have a box, it has state like number one with the half wave.
Well, if you only.
It should take the other
Yeah,
one,
it should take the other one S.
Why?
The one
because they're the same charge, so they,
Hunch rule.
You are too smart. Can we scroll back and speak at the language of freshmen?
they repel each other because they're the same charge.
It's off-boss principle and Hunch rule, which is.
Paul's principle?
I don't know.
What did he just say? What did he say? Oh,
You should teach each other. So what
I
about,
teach
teach me.
them a lot and they teach me a lot.
it's a perfect.
I only get taught, I don't know things,
That's not true.
You knew about voltammetry.
sort of.
You taught
Why
that.
did we do?
You taught as well.
Oh, man.
Anyway,
Back to the subject.
Back to subject. So electrons, what do they do to each other?
They
They're
repel.
repel each other
Okay,
because of their like charges.
what happens if we insist and place two electrons on the same state?
Energy will increase.
Energy increases due to the repulsion.
Right, what will be the value of energy?
Will it double?
Any other?
Square. What did you say? What was the question? What happens to what?
I know that
Q.
our interaction with Patricia started with the infant when she told like she doesn't understand.
Would it? Okay, I think energy would, yeah, actually it'd probably be squared, yeah.
Square, double, triple, what, any other?
V over two.
Logarithmically.
If we never see them coming together, this energy penalty should be very high. What is the highest number you know?
Infinity.
Yes.
Increases to infinity.
So, and even if you place recklessly without special measures, special mathematical tools, if you model placing two electrons even on different states, the energies of their interaction still will be infinite. One needs a special tool that Mother Nature applies anyway, but we are happy without knowing it. Oh, no. We need to pick the origin of the power exclusion principle on a mathematical language.
The polys, oh, yeah, yeah.
So what I really enjoy you bring in through this brainstorming session so many ideas that more than I can imagine, and a lot of them are correct. So
A
what's
lot of them. Man, where did the-
so what is the origin of power exclusion principle? You may have heard about it or
Oh my God, you're in Roger's lab. We learned it in Roger's lecture.
There's a lot that you got.
Vaguely.
All
No, I.
I feel like we've already talked about it in here.
Oh, just
no,
kidding.
here we didn't cover it.
Oh, man.
Yeah, I don't know what it is.
There, Pauli exclusion principle in quantum mechanics, the principle states that two or more identical particles with half integer spins cannot occupy the same quantum state. With the quantum. Okay, I know exactly what you're talking about. Yeah, so the first electron is gonna have like a half spin that's positive, the second's gonna have a half spin that's negative. And so they cancel out.
They have to spin the other way.
And so if you don't have any electrons, you have an uneven.
I don't know the origin.
This is perfect, but we formally we do not know what spin is yet. It is just another. So the power exclusion principle is a source of the Aufbau principle. When you do this, one is two, two is two, two be secret, and then keep going to. Instead of having one S 100.
Yeah.
So it's, you can only have
Okay, so that, and hope it can only contain 100.
whatever the orbital can take, right?
But there, I do not know how to introduce it. I can just repeat it as a pattern, or just give you a statement and ask to believe it, but maybe we can come with more reasons. What's the difference between bosons and fermions?
Between what now and how?
Fermions.
Fermions, we've never learned that.
I
I've
don't
never
know
heard that
what
word
that is.
before.
I don't know.
Electrons are fermions, vibrations, and excitations, and photons are bosons.
Okay, so
And pairs of electrons are also bosons. But the electrons,
pairs of electrons are
bosons,
bosons.
Bose-Einstein particles. But
Oh,
standalone electron is
Sam,
fermion.
BOSONS.
Bosons.
Boson.
Yes.
But right now,
So is it basically you have a single electron, which is ferron? I think I'm saying it.
Fermion.
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 Fermi, the Italian who came to the United States and built the first nuclear reactor in Chicago in
Okay,
1942.
so fermion,
Oh.
boson, whatever, F and B, F and B. So you have electrons are fermions and only electrons. are
Well, there are, if you do nuclear physics, high energy physics, there are many other.
fermions.
fermions, but
So,
in other real life, basically fermions are electrons.
Yeah.
okay, so for like simple, like for all intents and purposes, for like this class, an electron is the only thing we'll be doing. Okay, so you have an electron, which is a fermion, and everything else that we deal with basically is boson. Okay. Single electron acts as a particle.
They're too busy between each other, we need to involve them in discussion, so instead
No.
of.
Stuff about the discussion, we're trying to understand everything.
Why look it up?
Because matter, bosons make up forces.
You had to look that up, though. We could have gotten to that by
Okay,
talking.
and what's the statistics, what's the difference in statistics for bosons and fermions?
There's definitely way more bosons than,
Yeah, well, and you can measure mass.
In ground state, there could be infinite number of bosons, but only 2 electrons. Because the wave function of bosons is symmetric and the wave function of fermions is antisymmetric. So I would be very happy if you find any video on anti-symmetry of the wave function for fermions.
Looking it up,
Anti-symmetry,
anti-symmetry
that is not symmetry.
of fermions.
Yes.
Fermion?
Why fermions must be anti-symmetric. Yes, they're gonna be anti-symmetric.
Why they must be.
Okay.
Thank you to the author to this statement I just read because I. So what do you see?
Anti-symmetric, sorry.
So what about the anti-symmetric?
Fermions.
Over operations such as hydrogen, sure, there's some only food stuff here. Talks about matrices. It reduces the dimensions of the problem.
Any number of bosons can occupy the same state,
Yeah,
but no two fermions, so no two electrons, right? Can occupy the same state.
okay. And how the statement, which you already know is Pauli exclusion, relates to anti-symmetry of the wave function?
Because
We will get much better to the result and remember about it compared if I will start mounting something.
I was gonna say, if it comes to the Pauli exclusion principle and they can't share the same state, it means that in each orbital, so like your 1s1, you're gonna have one that's positive and one that's negative. They're gonna be the opposite. Like you're not gonna have two like positive half spins. You're gonna have, you know, and so for like your p orbitals, you'll have three different states,
It just be doing.
three positive one halves, three negative one halves, but each at a different energy level. I guess it's probably, I don't know if energy level maybe is the right term, but they're not, you're gonna have three positive half spins, but they're not gonna all have the same like value. And three negative half spins that won't have the same value. So none of them will hold the same like charge, or they'll be in the same, what was the term?
Anti-symmetry?
No, what was,
What's the number?
huh? Quantum number? They might have the same quantum number.
Well, I mean, nothing can have
They
the
can't have
same.
Energy
the same
state.
form.
They won't have the same energy state. Because as you move up the orbital, you're going to increase energy because you're increasing the number of electrons, even though they might be like in the orbital, you have a positive and negative half spin. You're increasing the number of particles that can be repelled. Does that make sense? Am I like on the right track?
There are grains of truth in your.
Hey, you know what? The fact that there's grains of truth within it, and I'm the only one, well, actually, I should say, that one, but
What does your bracelet say?
bitch.
Oh.
Okay, so I'll introduce the word that I do not know how to write. The word that I do not know how to write. So how do electrons charges interact with each other?
They will.
Repel or attract if they negative opposite?
They're opposite charges.
So who designed this law?
Mother Nature.
And who of humans declared it?
I don't
Boltzmann.
remember.
Oh, he doesn't.
Einstein.
No,
Dimitri.
no. Okay, so you need to teach me because
That was so
so
much.
I know that there are letters, this one,
Oh,
and
you.
then there is either both you or at one place.
No, it's you on the second
On
one.
the second one.
So not Coulomb, but Coulomb.
Kaloom.
Okay,
Column.
so,
Yeah.
so same as the European who came to the America?
Yes.
Okay.
What?
Do not mix them.
Columbus.
Columbus,
Not
No.
Columbus.
No,
Don't
it's
mistake
a you
Columbus
after the
first.
first one. That's a you after the first
first
one.
one, Coulomb,
And not after the second one.
this
Oh,
one,
Yeah,
Yeah.
so it's what I said the first time, and
okay.
I doubted myself.
So, I will chat about Coulomb. Then, we'll do an example, of two electrons in the same state, and, just get that it gets to infinity. Then we will introduce later then we got to energy of 2 electrons. And I think by this time, our time will be over. And then there are some slides with MATLAB. And in my teaching plan, this lecture should be on vibrations. Okay. So energy or 2 particles with charges Q1, Q2.
Coulomb's law.
Oh,
It's the inverse
yeah.
square law. R squared times
God.
K.
Okay,
Yes.
okay, enough.
Okay. Is that correct?
Yes.
I don't know.
Google tells me so.
Some people do 1/4 pi
Look at that, but,
Physics.
yeah, and that's what. Yes.
The electric constant is like
I
polarity
like
of
that
the solvent.
one, just because I
And
forgot.
in polar solvents, they stop interacting. So it is what secret knowledge that Patricia was witnessing on Friday's group meeting. Okay, now we do have the wave function first orbital of the first electron in the box. Normalization is something like square root over distance, maybe factor 2. I promise to do errors. Sine 1 times pi divided by Lx.
Why did you do 1 times pi and not just pi over L times X?
As a memory to myself, L equals 1.
Yeah.
Ah,
Your bees were.
I was just asking, don't get so hostile. Jeez.
Hostile.
So
I'll show you hostile. Beeswax, she's allergic.
Yeah.
if this is an operator, how to find expectation value of the Coulomb energy? So expectation value V, and we need to introduce that the wave function for the second electron. And we will assume falsely, we'll prove that it is very wrong, that it also resides in state 1. And it will be also square root 1 over L sine. And we need to use R1, let's do X1 because we have 1-dimensional things. So pi L X2. Why do we use X1 and X2?
Because 2 different divisions.
So they are independent. Even if you have 1-dimensional box, like suppose this is the box. Here is electron number 1, here is electron number 2. You are in the same box, but you have different positions. And then mathematically it becomes 2-dimensional problem because you can swap place, you can walk around the box. Okay, so we do need the way how to, if it is positions in 1 dimension, we will put only X here. And we need a matrix element. Like if we have an instrument to measure Coulomb energy of these 2 electrons in the states in the box, what will be the energy? It is way beyond our course. So we like electron number 1 in state 1, electron number 2 in state 1, electron number 1 in state 1, electron number 2 in state 1. So it is a matrix 2 brass and 2 cats because there are 2 electrons, right?
So Beeswax, I did not understand what you're saying.
Brian cat same as before. So bra cat. I don't have a different speech. I just repeat what I'm saying. Wait, in 3 months we will have a mathematical expression which will have operator A repeated several times. Okay, and we do it as phi 1 star x1 phi 1 star x2. This x1 minus x2 phi 1 x1 phi 1 x2, and then we have integral dx1 dx2. The only way, or the only goal I pose for torturing myself rather than you, because I will be deriving, is to show that this will be infinity, and we will need a trick. So what do I do? So I plug in the signs, right? And then expectation value of v dx1, dx2, sine square by x1 L, sine square by x2 L, x1 minus x2, dx1.
Is x1 minus x2 squared?
Huh? No. I was lying. If it is force, then it is square. If it is energy, then it is 1 over distance.
Okay.
Positive. Thank you for technology +1 because picking up an important point. Okay, and basically it will be infinity, but I need to prove it. I do not want, but I.
Sorry, can I have a question, Dimitri?
What?
I have a question.
Yes, please.
The integration part of the wave function, is it a derivation of what?
Please repeat.
This, let me come to the part. This is equal to this?
Yes.
Okay.
Okay, very good. And I don't know where to take the more pressure. I probably be still in the other classroom.
Need another expo marker. I will just go walk into that classroom and take one if you want.
Sorry, when this one, right out. So,
Yeah, thanks.
how do we do it?
Good question, Dimitri.
Bro, I don't know.
I think you start by integrating.
Yes, but why it is not so easy and why do you need tricks?
Because you have signs. And you have the x's in the signs, but you also have x's not in the signs.
Yeah,
That does seem tricky.
and then it's a double in, yeah. It's like,
Double, not the big problem. What I do not like from the first place, that here is a subtraction and here is everywhere x1, x2. So I would love to replace it to u equals x1 plus x2 and v equals x1 minus x2.
Okay,
Change variables.
okay,
And then maybe it will be more doable.
so. But if those are multiplied together, oh, actually, yeah, no. Trig laws.
And then we can do sine x1. I will just skip this part, otherwise I will die of writing too much. Sine x1, sine x2, and we need to convert it into trigonometric function of summation and subtraction. So what our trigonometry tells? What do I will waste all time. It's
Well,
we need 2 hours to complete even this thing.
can't
I don't.
you,
Just go into Wikipedia and look for.
Yeah, Google trig laws. Trig.
Or when it's sine squared.
Okay, sine alpha, sine beta equals 1/2 times cosine alpha minus beta minus cosine alpha plus beta.
Brilliant.
Whoa,
Whoa, we've never used that guide.
Is it? I just did it at home. So product of sine x1 sine x2 cosine subtraction minus cosine of summation. Is it what?
But it's times 1/2. That
Okay.
whole thing is times.
I'm not. I'm not.
Write that on there.
that's just a formality, we don't care.
Okay.
That's good.
And then our integral will be this little, right? So square of 2 cosines. Make sense? We can get back into business if instead of writing everything, I will just show my cheat sheets. Okay, now if we take a square, how many terms are we going to get? Square of two open brackets, four. Okay. So square of the first cosine, square of the second cosine, and maybe it's, then two terms can be combined together, -2 their product. Then we can consider each of the terms as a separate integral because there's too many efforts to deal with them, right? So the first one will be just cosine of the subtraction divided by subtraction, and here we can change the element of the area, like product of dx1 and dx2 can be 1/2 of the product of their difference and summation. If you find otherwise, please teach me. I will use it towards next year. So first integral is cosine of the subtraction. Second integral will be cosine of summation in the top, but still minus in the bottom. And the third one will be cosine of the products, right? So if we change the variables to u and v, then the first integral will be cosine square u divided by u, du dv, and then for the variable v, it will be just integral of like 1, right? Integral of 1 from 0 to L will be L, right? Therefore, and 1/2 is from what else I found, whatever, who found? You both found.
I found.
Okay, thank you. The 1/2 from trigonometric identity. So L over 2, and then if we need to take this integral, I'll postpone it and do a little later. The second one, we have cosine of v, cosine square of v divided by u, right? And then there are two independent variables. We can decompose it as integral du divided by u, which we will work, and integral of cosine square of v dv. And the third one will be cosine u cosine v divided by u, and so it will be like two integrals, one cosine v dv and another cosine u divided by u. So this is something we are progressing forward. Now, what do I do for the first integral? So, what is the Taylor expansion for cosine? Come on, it is a.
Like you have, but it's that,
Just say yes.
yeah.
Yeah,
I knew we have excellent interaction. But you recall it, any function can be reduced in Taylor series as a summation of polynomials. And in basic calculus, one does like Taylor expansion of exponential, sine and cosine.
yes.
Right? So if cosine is composed of each second power, like 0, power 0, power 2, power 4, and here are factorials. If we divide cosine u, oh, that's a little trick. If we take square of this, we can take like first square, then first times second, plus first times third, plus second squared. And if you carefully do it, the leading term will be 1 minus u squared. So we drop higher terms because contribution from the first one will dominate, and we will see infinity anyway. Right? I'm just doing a little exercise. So if you go from there, so it's our cosine u divided by u, and if we perform integration from the first term, it will be log, and from the second, it will be just power increases back to square divided by 2, right? So in some sense, we are done with the first integral. What about the second one? The second one was so from integration, second one bases on the trigonometric expansion of cosine square into double argument, which you also expected to remember or being able to find in the Wikipedia, right? And then we have two, back. We do have two independent integrals. Yeah. One over du over u, and another is cosine v squared dv. If you take this integral from the u du, we have log, and by integrating cosine square expanded over this thing, we'll get v from the first one, and then sine 2v from integrating cosine. And if we plug in the specific values, we will get the so this one quarter is just combination of factors. So we have log L minus log 0, and then there will be L sine of at the edges of box is 0. Okay, and the third one will bring it back. The third one includes integral of cosine dv. Integral of cosine is what?
Negative.
Sine.
No, it's just regular sine.
Regular sine.
Sorry.
Okay. And sine at the edges of the box. It was our boundary condition. Sine of 0, 0. Sine of if we bring back this pi divided by L, so sine of at the opposite edge will be also 0. Like pi 2 sine 2 pi is also 0. So this part is 0, and then we do not need to take the second integral, right? So the third integral is completely removed. And then the summation of the three integrals from the first one, we do have size of the box log of the size of the box log 0, plus another term. From the second one, we have same expressions. Size of the box log size, and then size of the box log 0. So we do have minus 1/2 and plus 1/4, but as a result, it will be minus 1/4 of L log 0. Because what is log 0?
One.
Log of 0 is.
Log of 0.
Yeah, can you draw exponential? Can you draw a function of exponential? Function of exponential grows infinitely, drops down to 0 or negative, right? And comes
And
from
anything to the power of 0 is.
No.
1.
now. Log is obtained from exponential by mirror symmetry along x equals y, right? So it will be this way. So when we have log of 1 will be 0, and log of 0 will be
Oh.
Log of 1 is 0. Log of. I don't know.
log
Log
of
of
0.
zero is
Just do not think it is useless. Just look on the figure.
It's either negative infinity or undefined.
Like, here are my x's. 0 is here. Where this line goes?
Almost 0.
No, line goes
Going
to,
down to
Down.
negative
Yeah.
infinity.
so negative infinity,
Yeah.
right? So the value of this integral will be, so minus 1/4 times L times negative infinity. Minus time minus will be plus, so it will be plus infinity.
Ah, infinity.
Okay. I don't know how about other things, but at least we went through this thing. Okay, so now you do.
Why did I think so strongly that logom?
I don't know. No, I was with you.
So we got through manipulations, we proved that the energy will be equal zero. Oh, no, not zero, infinity.
Yeah.
Equals infinity means it is impossible because we do not have enough resources to communicate. The rest is easy.
Don't worry.
Oh, I read it in his eyes. I came here not for this exhaustive equation. Where are my jokes? It's boring. Stop writing equations, otherwise I will lose the class.
I'm not gonna leave. No,
But I will change my opinion about the instructor.
No.
no.
Maybe about the material, but never about the instructor.
Okay, I'm walking on a thin ice. We're showing more than 3 equations per piece.
It's okay.
Yeah. Come on, Dimitri. This is too hard for us, for simpletons.
So, even if we plug in here the second function, according to your FALL2022, we still will get infinity. It still will not work. So just placing second electron in second place will not help. We need another trick. And I am going to introduce
Later.
later.
Did anyone use later?
When I was a postdoc at the University of Florida, I was sitting in as is due for subordinates in the office without windows.
Wait,
Yeah.
University of Florida in Gainesville?
Yes, engaged.
Oh, Lord.
And across the door from my office, there was a watercolor painting written, created by John Slater at his leisure time when he was emeritus faculty at the University of Florida. So it's my closest connection to this. So I can erase. Who is this?
Why were you, what's the,
Oh, there's just some.
you have beef with some random university in Florida?
No, there's just something with.
Is
my
it a crack?
fraternity there.
Yes.
My fraternity has a bit of.
X1, X2. Right now,
All those things.
we were assuming that if we have first electron and second electron, they are the wave function of this combined system will be just X1, X2, just a product of them because they are independent functions, right? And Slater told that it is wrong. We will always get infinite energies and our energy will experience Coulomb explosion. Nothing can stay together. Everything will explode to minimize energy. Just Coulomb. So here is the trick. I started hating all natural sciences and all my instructors when they were trying to teach me the following equation. I hated it from childhood. So no, it should be
Okay.
according to phi1 x1 phi2 x2 minus phi2 x1 phi1 x2. This is the equation I hated for many years, and maybe my hate isn't stopped even now.
But doesn't that just equal 0?
No. That's
Or it's psi 1 of x1, 2 of x2, and then psi 2 of x1.
Yeah, but if you multiply two numbers together.
They're not the same numbers. Yeah, it's different functions.
Oh,
with
I see.
different-
see, like here is the same argument, but there are different functions. Okay, no, so what happens if we swap the order of the electrons? So if you write psi of x2, x1.
Would I just switch
Wouldn't
the
it just
sign
be-
of what's in the parentheses?
Probably Melody is not hating Slater.
Yeah, Melody loves Slater.
So we have by 1x2 by 2x1 minus by 2x2 by 1x1. And this, as Melody absolutely correctly told, it will be minus psi of x1, x2. So swapping indices is symmetry. If swapping indices will not change anything, function will be symmetric. But if it by swapping indices it changes sign, it is anti-symmetric. So anti-symmetry of the wave function is mathematical reason for power exclusion principle. And it is a discovery of John Slater that allows our world to exist, not to explode. So it and now in the remaining 3 minutes, at least I will finish these things. But you got the idea.
Yeah.
And I'm proud of you just for staying patient to the thing. You're way ahead of any undergraduates in the whole world. It's typically credit to you.
Yeah.
Maybe sometimes to the very top students in physics, but not everyone. But you're above.
In the whole world.
Case.
Hey.
Right.
No,
So
contributed much today.
That's okay. You have any work to worry about.
I slept through my biochem this morning. I stayed up.
just want to bring up. Oh, okay, yeah, very good. Oh, and in the remaining couple of minutes, I will quickly jump through a couple of slides. Yes?
Can't see us.
High five.
Good every time.
It really is.
And actually, we even do not start lecture 24. We do just little comment that I designed in the middle of the. Those are concepts. Okay, interesting. This is your homework.
That's the homework.
Uh,
Homework answers.
Okay,
Where?
no, I will bring answers next time.
I was asking
So,
if they could.
the equations that you have just observed on the screen.
Yeah.
Now you're in the remaining minute, your mind will boil and blow
Oh. It does that every time in this class.
up. You know, if you make it more dramatic.
Okay,
So
I'm ready.
the equation write it in a line, and this symmetric wave function can be written as a matrix, right? And if you take a determinant of this matrix, you'll get exactly Slater function, right?
Yeah.
So if you do have phi 1, phi 2, phi 1, phi 2, and here is 1, 2, 1, 2. If you take a determinant, it will be phi 1 R1, phi 2 R2, minus phi 2 R1 times phi 1 R2. You see it?
That's
Yeah.
that.
Exactly. Therefore, it is the equation is called Slater determinant. So now you know what Slater determinant is. Now, the next thing. If we plug in our Coulomb matrix element, if you want to find expectation of value of 2 electrons in the box, and we will, instead of being only product, as we did before, it will be Slater determinant for Brian Fouquet. So, bracket. It will bring us back to normal world. The result will be not infinity. And of course, I'm not going to derive, even simplest thing took us like 30 minutes.
Yeah.
So here is something that we can
Fun
we will
demonstration.
do on our lab. So multiply one sign times another.
You gonna do that on Wednesday?
Yeah. If you swap the order, it will be this one, right?
We're not stuck in lab until.
If we compose product of sign of the first state, second state for different functions, and then we swap the order. It will be this two things. If we subtract them, the nodal plane will be not along the axis, but along the line x equal y. And it will be 0 along this line. Equals 0 is critically important. Now, and if we swap the order, it will be antisymmetric. Orange will change to blue, blue will change to orange.
Does that mean that every line is going to be 0 that like cuts it in half? Or is it just
Only this line will be
only
blue.
when it's diagonal?
What does
Yes.
that mean, the line?
Not when it's horizontal or.
Orange means positive, blue means negative,
So in
green
between
means
there,
0.
zero.
Okay,
Oh.
so every like midpoint between.
You see, here is the color map.
We need the,
Oh,
we needed the colors.
Oh,
That
Okay,
makes-
now, if we multiply our wave function by Coulomb term has discontinuity when they are equal to each other, right?
Mhm.
So if we multiply wave functions by Coulomb, this product will have discontinuity, and even if we integrate it carefully, the result will be not a number, so we will mathematically get infinity. That's the exercise that I keep doing. Not a number, means
You're
infinity.
telling me that doesn't say sodium nitrogen?
No. NaN in MATLAB means not a number, so it tells I cannot accommodate it. It's something crazy, which means infinity. And if we plug in the antisymmetric wave function, take its absolute value squared, then it will be zeros on the main diagonal and positives outside, multiplied by this Coulombic thing and integrate, the result will be something valuable, really small. So their interaction will be not infinity. And it is a indirect proof that antisymmetrization of the wave function allows us to live.
So does it get a different small number depending on the values of the variables, or is it always gonna be that same number?
The value of Coulomb interaction, or the matrix of element of Coulomb interaction, will depend on the system and orbitals. It is not universal. It is need to be recomputed again and again.
Okay.
Okay?
don't need to get it. I'm not with numbers.
But-
No rocket science.
So
Get it.
Oh, it's.
I think we are done.
Meeting is done?
Yes, meeting is done. We do. I'm over time. And looking forward to see you where on Wednesday. Yes. How do we show?
Meeting is done.
My ability.